Welcome to this second video tutorial about RapidMiner. In this video tutorial we're going to cover functionality related to data exploration. After we get a dataset, the first thing we should do is try to understand what exactly the data that we have in the dataset it is, and trying to see different issues or opportunities to improve the data that we have in the dataset. Let's start with one of the datasets that RapidMiner has already integrated in the environment, which is the weather dataset, the one related to the weather conditions and whether we play or not the golf game. If we run the process, in these results here we have a tabular representation of all the data present in the dataset, and down here we have information about the dataset. We have 14 examples. Examples is the name that RapidMiner uses for each of the instances. Each of the instances is represented by a feature vector. It will be one row in this table. In RapidMiner they are called examples. We have one special attribute. The special attribute in this case is the label, the class, what we would like to predict, whether we play or not, and 4 regular attributes, which are outlook, temperature, humidity, and wind. For a real-world dataset, visualizing all the dataset is not something we're going to be able to accomplish. Here it fits just in this screen, but in the real world it will be a much larger dataset, and we may be interested in exploring some statistics about the dataset. I'm going to right-click here and maximize the tab. In these statistics we can see some summary about the different attributes in the dataset. For example, the label play is telling us that is of type nominal. It has 0 missing values, so it's present for all the instances. I have 5 values of no for the label and 9 values of yes. In the case of outlook, it's also nominal. I have 4 overcast, is the least frequent one. I have 5 rainy. I also have some sunny. Here if I click on outlook I will see an histogram describing the values of the attribute outlook. If I go back to statistics, I can see that temperature in this version of the golf dataset is numeric and is also showing a histogram, and is showing here the minimum temperature 64 Fahrenheit, the maximum 85 Fahrenheit, and the average. It's also showing the standard deviation, which is 6.5. And the same for humidity, and wind is also a label in this dataset. Let's go back to the design tab and let's drag the iris dataset, which is a more realistic dataset with 150 real measurements of iris flower. I'm going to run it, and if I go to the statistics statistic button here, I will see statistics about the class, which I'm still in the golf dataset. I have to change to the iris, right click, maximize. I'll go to statistics. I see here that I have the ID, which I don't really care too much about because it will be omitted in any analysis, and the label here, it has 3 different values, iris Virginia, iris setosa, and iris versicolor. I can see in the histogram that the proportions of each of the 3 types of flowers is the same. And I can see here for each of my attributes the minimum, maximum, and average value, and if I click here I'll be also able to see the standard deviation. I can visualize this data by checking the different representations that we have covered throughout the course. I can accomplish this by using the third button in this slide, which are the charts one. For example, if I go to charts, let's select first the histogram representation. Here I can plot histograms of the different attributes. By default you probably have an opaqueness of 100%. This is interesting when we are plotting histograms of different attributes at the same time. Right now I have 3 histograms here, the one of the attribute A1, A2, and A3, and I cannot really see the shape, for example, of the attribute A3, the red one, because it's covered by green and blue. If I decrease the opaqueness, I'll be able to see through the beans, and I can see the shape of the red histogram. I can also change the number of beans in the histogram to make them less beans or more beans and have more or less detail about the shape of the different distributions. If I check here, for example, the attribute A1, I cannot really see any clear patterns in the distribution of the data, or especially in A2. So in this case, I cannot really affirm that I have different types of flowers based just on the value of this attribute. But if I check A3, I see here a gap in the middle of the histogram. So it's clear that by using a single partition based on the value of A3, I can distinguish these flowers over here from these other flowers over here. So I clearly have two different groups of flowers based on this attribute. If I go here to histogram color, the graphs that RapidMiner has, which have the surnamed color, whatever color, that color is based on the class. So for example, here, let's increase the opaqueness. Here I can see three different colors. In this case, they are not three different histograms for different attributes. I'm only seeing the histogram for A1, but here is showing me independently the iris setosa, iris versicolor, and iris virginia. For example, over the A2 attribute, everything is pretty much mixed. There are regions where I can see the three colors overlapping each other. But if I go to the attribute A3, I can see that all the blue is in this region over here, that's iris setosa. Most of the green is here, and there is a small overlap with the red. The red is iris virginia, and the green is iris versicolor. Visually, this is giving me information that the attribute A3 is going to be useful, especially for distinguish iris setosa, and way more useful than, for example, the attribute A2. After checking plots of each attribute at a time, I may want to move to scatter plots or the scatter matrix. In the scatter matrix, I can see the scatter plots of all the pair of features in my dataset. Here again, it's using colors to distinguish among the three different types of flowers. I can see visually, for example, that A1 and A2, there is no very clear patterns here. I may be able to distinguish the blue from the other two, but the other two seems to be quite mixed here. However, using A1 and A3, I could very easily tell apart the blue flowers, which I think I remember they were iris setosa. I can also see that I have very strong correlations, especially between A3 and A4. If I have a very strong correlation, it means the information that is being provided by both those attributes is highly redundant, and I may have opportunity to decrease the dimensionality of my dataset by using techniques such as principal component analysis or linear discriminant analysis. If I want to see more detail, for example A3 and A4, I may go here instead to scatter matrix, to the scatter plot, and I could plot, for example, A1 versus A3. And I can see how there is a high linear correlation and how all the iris setosa is in this region, and there is a little bit of overlap between Virginia and versicolor. If you counted the number of dots here, you will realize that we don't have 150 dots, and the iris dataset has 150 flowers. The reason is that the discretization measurement from the length and the width of the sepals is quite big, and a lot of flowers have exactly the same measurements. If we add jitter, we're going to add a small random noise to each of the points in the datasets, and we're going to start seeing how some points are separating from each other. By adding small random values, if I add enough value large enough, right now I'm probably seeing the 150 different values. It's useful especially when we have either such as in this case a big discretization factor for the measurements. We don't have a lot of precision and we have a lot of measurement with the same measure, and especially useful when we are visualizing labels, as we'll see in another dataset later. Another representation which is quite useful is the box plot. In the box plot representation we can see box plots for all the different attributes. Let's forget about the ID. These are the 4 attributes for the weather dataset. And for example, by visually exploring the data, I can see that it is possible I may have some outliers. So maybe I would like to check using some statistical criteria whether these are outliers or not. And while A1 and A2 seems to be more or less normal data, A3 is clearly not normal data. I can see this because the median, which is this bar in the middle, is very close to the third quartile and very far from the first quartile, while here the median is more or less in the middle of both quartiles. If we go back to the histograms, and if we plot A1, we can see how this distribution is more or less normal, not really, but it could resemble something normal. A2 is also more or less normal, but A3, which was the one where the median in the box plot was very far from one quartile and very close to the other, in this case we can see that this is not at all a normal distribution. Best case scenario could be 2 different normal distributions, but not a single normal distribution. Another of the representation we have covered in the course is parallel plot. In the parallel plot we have different poles, for one pole for each of the features, and each of these lines is representing one instance. So that value over there is connected with this value down here, with some other value over here, with some other value down here. By following each of these lines we will have the values for each of the 4 features for this dataset. You remember from the theoretical sessions, the fact that there is disorder here is showing that there is lack of correlation between A1 and A2, and that means they are providing non-redundant information. The fact that there is a lot of order here between A3 and A4, for example, this order is showing high correlation about A1 and A2. For example, we go to the scatter plots, we plot A1 and A2, we see pretty much a shapeless cloud. There is no correlation among that data. However, if we plot A3 and A4, we see a very high correlation among these 2 features. That way we saw that regularity in the scatter plot. There are other representations. For example, we have a 3-dimensional scatter plot. We represent, for example, A1, A2 and A3, and we can drag with the mouse this 3-dimensional representation of the data. It's not really, of course, 3-dimensional, but we can just change different 2-dimensional projections, because after all the screen of the computer it just has 2 dimensions, but it may be useful in some cases. We're going to go back to the designer. I'm going to import into RapidMiner another dataset from the ones which are preloaded with the tool. In this case it's going to be the Titanic dataset. It's information about the passengers of the Titanic. I'm going to drag here the dataset. I'm going to connect it here and run the process again, and I'm going to maximize the tab. In this case it's telling me I have 1,309 examples. Those are instances. Those in this case are passengers of the Titanic. I have 0 special attributes and I have 12 regular attributes. So I just have no label in this dataset. In this dataset I have question marks, such as for example here. Question mark is how RapidMiner represents a missing value. That question mark over there means we don't really know, in this case, the cabin in which the passenger corresponding with the row 14 was traveling into the Titanic. If I go here to this combo box over here and instead showing all the data, I select here show no missing attributes. It's showing me only the instances for which I have no missing values and no missing no missing attributes. It's showing me just the instances and the rows for which I have no missing values. So this will be the attributes for which I do have all the values for all the instances. In this case, I have 180 instances for which I have complete information. If I click here on missing attributes, I have the remaining 1129 instances for which something is missing. So this is a very interesting piece of information. For the vast majority of the passengers, I have some piece of data which is missing. If I go here to charts, and for example I want to create a scatter plot of whether they survive or not, and the gender of the passenger, I see absolutely nothing. I see just 4 dots in this scatter plot. Those 4 dots are really the 1300 passengers, but given that each nominal attribute in each axis only has 2 possible values, I only have 4 points in the feature space where my instances may fall. If I add jitter here, suddenly I do see a little bit of, I have information about how many instances do I have here, how many other instances do I have over there. And let's, for example, ignore the color, because the color here is I have no easy way of ignoring the color because it wants to use something as a color, but let's use survive as a color. And for example, I can see that most women survive. This is survive, yes, and here I have more dots, more instances than over there. So most women have survived, and most men, these are the male, have not survived. Very few men have actually survived if we compute the proportions. However, most women, these are the women who survived, these are the ones who died. Most women survived, most men died. This is something I can realize by exploring the data visually. So for example, if my goal in this dataset was try to predict whether a passenger is going to survive or not, knowing the sex is a quite relevant piece of information based on that plot. I'm going to go back to the designer. I'm going to import one last dataset. Is a WCA format dataset, ARFF file. I drag here the operator to load the file, and I need to configure the path of the file in my local file system. So you need to navigate to wherever you have uncompressed the data.zip file. You need to go within the classification folder, and we're going to load the Wisconsin database breast cancer, which is another database related to tissue samples. If I open it and I run the process here, I maximize it. The class here is a piece of information which is telling me whether a lump in the breast of the woman was a malign tumor or was a benign tumor. So I may change the role of that attribute. I may change the role of the class from a regular attribute to a label. And now it's shown here in green. And if, for example, I generate a few scatter plots, scatter matrix, the whole scatter matrix, I'm going to realize that in this data set there are very strong correlations among some of the features, and some of them seem to be non-linear correlations, such as, for example, the correlation between A3 and A4. This seems like a curve, and also A1 and A4 seems like a curve, non-linear correlations. And in general, in this data set, while there are some data which do not have, don't seem to be correlated, A1 and A9, given this plot, seems to have very low correlation, but A4 and A8 and A3 and A8 also seems to be strongly correlated, not as correlated as the one we saw at the beginning, but here again we have very strongly non-linear correlated features. This dataset has a lot of correlations. Let's go back to the designer. Let's see exactly how much correlation there is among the data by computing the correlation matrix. If I drag here the correlation matrix operator, I'm going to connect the matrix output to the output of the process so I can see the value of the correlation matrix. And I just drag this. Just maximize because it's very large correlation matrix. The darker the cells are shown in this representation, the higher the correlation it is. And indeed I see how I have values of correlation of 0.998, extremely high correlations. Of course, in the diagonal of the matrix I have ones because every feature is perfectly correlated with itself, but outside the diagonal I have very high values. 0.5 is already high, but here I have a lot of 0.8s and even 0.9s, so I have an extremely correlated dataset. This is good in some respect because this dataset is a dataset where I have 569 samples. I have 569 samples taken from lamps in breast of women, and I have 30 attributes. 30 square is 900. The number of dimensions raised to the square is way larger than the number of instances I have. I have too many dimensions. It's very likely I'm going to find patterns in this dataset which are due to the high volume of the feature space and low number of samples and not true regularity in my data. That's why I say that it's kind of good that I have so high correlations, because having so high correlations enables me to try to reduce the number of dimensions of the feature space by applying some techniques such as, for example, principal component analysis or linear discriminant analysis. We are done with this video now. We'll move to the next video to feature transformation, where we'll see how to transform features and apply techniques such as principal component analysis. Before that, you may want to save this process that we have built in the local repository. You may call it, for example, exploration of data. And in this way will be safe in the local repository as a process, and you'll have it available next time you want to refresh what we have covered in this video tutorial. See you in the third video.